We are finally to Chapter 11, and we're going to start with redox reaction terminology. Chapter 11 concerns oxidation and reduction, and it's a part of our everyday life. We have to use oxidation and reduction in order to keep our bodies running with food as fuel. We certainly need batteries to get through our day, either rechargeable ones or single-use ones. How many of us would be lost without our smartphone? Of course, rust occurs and we need to fight against it, and hydrogen-powered cars are on the market. To describe redox to you, I first need to contrast it with precipitation. If we have solutions of potassium iodide and lead 2 nitrate, potassium nitrate will not precipitate, but lead 2 with iodide has a reaction. When we write that net reaction, we start with lead 2 plus ion in the aqueous phase and 2 iodide ions in the aqueous phase, going to our neutral precipitate lead 2 iodide, which is in the solid phase. Let's assign oxidation numbers to each atom or ion below. For lead 2 plus, for a monoatomic ion, the oxidation number is as it appears, +2. So that would be true for the iodide as well. For the ionic compound, the oxidation states have not changed. Lead is 2 plus, and iodide is 1 minus. So for precipitation reactions, there's no change in the oxidation number. Redox reactions are different, of course. Let's look at what happens when an iron wire is placed in a solution of copper 2 sulfate. This is fast speed, so I'll try and explain. This is a blue solution against a yellow background, so it appears green. But notice how the green color fades as the reaction proceeds. And also notice that we have formed some orangish material that looks suspiciously like copper. What is occurring in this reaction? First, the copper 2 sulfate is a soluble material. So if we start with a solid, we will make a solution of copper 2 plus and sulfate 2 minus. The copper 2 plus has a blue color. Maybe you remember that from lab. Next, we have copper 2 plus interacting with our iron wire. What is happening is the orange solid that you see forming is copper solid, and the color fades because the copper 2 plus is reacting to become the solid. The iron is reacting to make iron 2 plus, the ion in solution, which is colorless. So the blue color fades, and the orange solid replaces the gray solid. Let's look at the oxidation states for this reaction. Copper is in the +2 oxidation state. Iron is an element in its solid state, so that would be oxidation state 0. Copper would be 0 oxidation state, and iron would be a 2 plus oxidation state. So the copper is going from +2 to 0 oxidation state. This is different than precipitation because the oxidation state has changed. In order to go from +2 to 0, we need to gain 2 electrons. Electrons are negative. +2 and a -2 give 0. When this happens, we say the copper 2 plus has been reduced. Reduced because it's gone down in oxidation state. Going from +2 to 0 is mathematically going down in value. So the copper 2 plus has been reduced. On the iron side of the pair, iron is going from 0 to +2. That is because it lost 2 electrons. So if you start with 0 and lose 2 negative charges, the charge goes to +2. I suppose we could call that gained, but this is typically called being oxidized. The iron has been oxidized to iron 2 plus. So redox reactions have a change in the oxidation numbers. Now there is one terminology issue internationally by all redox chemists that tends to drive chemistry students crazy. The material that gained 2 electrons and was reduced is called the oxidizing agent or the oxidant. The copper 2 plus is named for what it does to the iron. It oxidizes the iron. And as you might imagine, the material that loses 2 electrons and is oxidized is called the reducing agent or reductant. The iron is named for what it did to the copper 2 plus. It's named for its action on something else. So to clarify these terms, the oxidizing agent is itself reduced. So we can write a reduction half reaction for our oxidizing agent. So remember that our oxidizing agent is the copper 2 plus. This is what's known as a reduction half reaction. Copper 2 plus 2 electrons going to copper. The copper 2 plus is indeed being reduced. It is gaining electrons. That is characteristic of the reduction half reaction where electrons are gained. And also the oxidation number of the copper 2 plus becomes more negative, going from +2 to 0. So when we gain electrons, they belong on the reactant side of the equation. You notice how this is just a little mini balanced reaction. Atoms in equal atoms out. Charge in equal charge out. The reducing agent is itself oxidized. So we can write an oxidation half reaction for that. This would be the iron. The iron goes from iron solid to iron 2 plus ion and loses 2 electrons. So in the oxidation half reaction, we lose electrons and the oxidation number becomes more positive. That means it goes from 0 to +2. Notice that when we lose electrons, they wind up on the product side. Also, notice this is again a little mini balanced reaction. Atoms in equal atoms out. Charge in equal charge out. You can use mnemonic devices to remember some of these definitions. Those of you from high school chemistry may remember oil rig. That reminds students that the oxidation half reaction is losing electrons, or even the process of oxidation is losing electrons, and the reduction half reaction is gaining electrons. Or maybe your chemistry teacher used Leo says grr because lions will growl. Same idea, losing electrons oxidation, gaining electrons reduction. Since we are at NC State, located in Raleigh, North Carolina, we have our own mnemonic device that we can use. This is Raleigh, but replace the H with an O. So Raleigh. This is the reducing agent loses electrons, it gets oxidized. So you notice how we have oxidize, lose electrons, which is true. And it also reminds you that the reducing agent is the substance that gets oxidized. It's also been suggested that you can use SPY versus SPY. So the reducing agent is the secret agent that reduces something else. And to do that, it gets oxidized. We should remember that for a spontaneous reaction, that reducing agent is on the reactant side. We'll get more into that soon. Let's go back to our example of the iron wire in copper sulfate. Here is the reduction reaction for the copper 2 plus. Remember that for the reduction reaction, which is gaining electrons, the electrons are on the reactant side. This is our oxidation half reaction. And for oxidation, that is losing electrons, so they will be on the product side. Here is the mini reaction that is happening to the iron. You may notice that the top reaction has 2 electrons going in, and the bottom reaction has 2 electrons going out. So if we were to add these reactions, those electrons would cancel out to 0, and we would be left with copper 2 plus iron going to copper and iron 2 plus. Exactly the redox reaction we observed. This is what's known as a net redox reaction. So here is the same exercise, but in a little bit slower motion. Can you write the oxidation half reaction, the reduction half reaction, and what is the oxidizing agent? We need to start by getting the oxidation state of the materials involved. Now that I have the oxidation states, the elements are at 0 oxidation states. The monoatomic ions are at the oxidation state of their charge. Let's look at the two pairs. We have zinc at 0 oxidation state going to +2. We have nickel 2 plus going to oxidation state 0. So let's first look at the zinc. It is going from 0 to +2. Would you say the zinc has been reduced or oxidized? I hope you're going to say that the zinc is being oxidized because it is going up in oxidation state from 0 to +2. So that helps us with our first question. Can you write the oxidation half reaction? Remember that oxidation is losing electrons and reduction is gaining. So our oxidation half reaction will be losing electrons. And if you can't remember that or have trouble, remember that these reactions need to be balanced. Is this a balanced reaction if we put the 2 electrons on the reactant side? Well, no, because we are going from a -2 charge to a +2 charge. So our 2 electrons belong on the product side. Here is our oxidation half reaction using the note template. Now let's look at the reduction half reaction. This has to involve the nickel 2 plus because it is going from a +2 oxidation state to 0. So we would say that the nickel 2 plus has been reduced. Remember that the reduction half reaction is gaining electrons. But again, if that's difficult, let's look at this without the electrons first. We'll start with nickel 2 plus aqueous going to nickel solid. Does it make sense to put the 2 electrons on the product side? I hope you say no, because the charge goes from +2 to -2. It makes much more sense to put the 2 electrons on the reactant side. Now we have a net charge of 0 going to a net charge of 0 on the product side. Our last question is, what is the oxidizing agent? What do we need to remember about the oxidizing agent? It gets reduced. So looking at my notes here, I believe that is the nickel 2 plus. It got reduced, and the zinc was the material that was oxidized. So remember, the oxidizing agent is named for what it does to the other substance in the reaction. So the oxidizing agent gets reduced, and our answer is nickel 2 plus. And of course, if we were asked who is the reducing agent, that would be the zinc solid. Remember that both agents need to be reactants. I hope that was better in slow motion. Our environment is just one big redox reaction. Animals use respiration to oxidize food for energy. That's known as respiration. And our solar cells, otherwise known as plants, reduce carbon to form glucose in a process known as photosynthesis. So we're all just one big redox cycle and dependent on each other. So speaking of oxidation of sugar, let's look at a reaction and identify the oxidizing and reducing agents. This, of course, means we need to know whose oxidation number has changed. Chapter 4 was much more important than you realize. Let me briefly go over the oxidation state rules to remind you of them. Remember that for Rule 1, the oxidation number of atoms in the elemental form is 0. For Rule 2, fluorine is always assigned an oxidation number of -1 when it's in a compound with anything else but fluorine. Remember that these rules have a priority, and Rule 1 takes precedence over Rule 2. Rule 3 says the oxidation number of group 1A metals is always +1. The oxidation number of group 2A metals is always +2. And the cheese stands alone. The oxidation number of aluminium in a compound is always +3. Rule 4 concerns hydrogen. When bonded to nonmetals, it is +1. When bonded to most metals, it is -1. And when bonded to itself in hydrogen gas, H2, the oxidation state is 0, because Rule 1 takes precedence. Rule 5 says the oxidation number of oxygen is -2, except when higher rules apply. And Rule 6, the oxidation number of halogens is -1. Other elements take their cues from these rules, and of course the rules must be applied in priority order. So what are some good candidates? Well, atoms in elemental form surely are good candidates to change their oxidation state. Transition elements, something like iron that can be +2 or +3. The central atom of polyatomic ions, like the nitrogen in nitrate, which is +5, going to nitrite, which is +3. Less likely candidates, but not impossible, O2- or H1+. A lot of times, redox reactions involve these two elements in the form of water, simply to balance atoms in, equal atoms out. So back to our question. Here is a respiration reaction, and we want to identify the oxidizing and reducing agents. So let's get our oxidation number. Hydrogen is the first rule we come across, and that, when bonded to nonmetals, is +1. Oxygen is the next rule, and that is -2. At this point, we have +22 and -22. So carbon will be 0 oxidation state. Oxygen here is in its elemental form, so that's a 0. Oxygen in this compound is a -2, making the carbon a +4. And for water, hydrogen is +1, oxygen is -2. Let's look at the carbon transition first. Carbon in our sugar is 0 and goes to +4. And there are actually 12 carbon atoms on each side, so there are 12 carbon atoms at 0 going to 12 that are +4. What is happening to this carbon? Is it being oxidized or reduced? I hope you think it's being oxidized, and oxidation is losing electrons. So we have actually lost 48 electrons over all 12 carbons. Since the carbon is oxidized, what agent is it? It is the reducing agent. So the carbon in our sugar is the reducing agent. This next part might be a little confusing because we have two different oxidation states on the reactant side. 11 oxygens at -2 and 24 oxygens at 0. But you notice we also have another 11 oxygens at -2, so we can remove those from our focus. Instead, let's look at our 24 oxygens that go from 0 oxidation state to -2. There are 24 oxygens that go from 0 to -2. So what is happening to that oxygen? Well, its oxidation state has gone down, so I hope you believe that it has gained 48 electrons. Because when oxidation state goes down, we are reduced, and that means gaining electrons. Oxygen is reduced and is therefore the oxidizing agent. Now I hope you realize where the term oxidized comes from. Oxygen is a great oxidizer of many different materials. One last thing about the electron count here. You notice how for the reducing agent we have lost 48 electrons, and for the oxidizing agent we have gained 48 electrons. It's important in these reactions that the number of electrons lost is equal to the number of electrons gained. Here is another somewhat complex question. We want to identify the oxidizing agent and the reducing agent. So once again, let's get our oxidation states. Copper as the element has oxidation state 0. Rule 5 says that oxygen is -2, which means the nitrogen must be +5 in order for this ion to have a -1 charge. H1+ is a monoatomic ion, so the charge is the oxidation state. Same with the copper 2+. For NO, oxygen is -2, nitrogen must be a +2, and water you have already seen as +1 and -1. Let's remember that the oxidizing agent gets reduced. Now looking at what's going on, we have copper going from 0 to +2. That's not it. Nitrogen going from +5 to +2. There it is. +5 to +2 is going down in oxidation state. We have 2 nitrogens at +5 going to 2 nitrogens at +2. So this gains 6 electrons and is reduced, making it our oxidizing agent. The nitrogen in the nitrate ion is our oxidizing agent. Let's move on to our reducing agent. Our reducing agent gets oxidized. And hopefully you're looking at the copper, which is at 0 and going to +2. So we have 3 coppers at 0 going to 3 coppers at +2. That means they have lost 6 electrons collectively. The copper has been oxidized, making it the reducing agent. Moving on in this question, let's identify the oxidation half reaction and the reduction half reaction. Remember oil rig. Oxidation is losing electrons, reduction is gaining. So our oxidation half reaction is very easy. This would be our copper, which goes from 0 to +2. Taking out the stoichiometry from the reaction and simplifying this, this would be copper solid going to copper 2+ +2 electrons. What about the reduction half reaction? This involves the nitrate. Taking the stoichiometry from the reaction away, a student might put down nitrate plus 3 electrons going to nitrogen monoxide. But you notice that's not really a balanced reaction. Our curriculum does not require students to balance redox half reactions, so you'll be given a table to look it up. It turns out that this is the balanced half reaction for reduction of nitrate in acid. You notice this is a balanced mini reaction. Atoms in equal atoms out, charge in equal charge out. So sometimes redox half reactions will need additional elements that participate in the reaction but not the redox. We had to have this because it was going from 3 oxygen atoms to 1 oxygen atom, so there had to be a way to balance the oxygen. Here begins your set of student questions. We want to know first, what is the reducing agent and the oxidizing agent in the reaction below? So please get the oxidation states of the materials involved and then choose the ones that fit the definition. How many electrons are transferred? For this, students should report either the electrons lost or the electrons gained, not both. The reason for that is we can think about electron transfer as maybe moving money from your checking account to your savings account. Suppose you have $5 in your checking account and $10 in your savings account, and you want to move $2 from savings to checking. Well, that means your checking goes up to 7 and your savings goes down to 8. Now the change was $4. Checking went up by 2 and savings went down, but you wouldn't say that $4 were transferred. You would say $2 are transferred. So look at either the electron exchange from reactant to product using the iron, and make sure you recognize that there are 2 of them, or the electron change from chlorine to chloride, recognizing that there are 6 of them.